All right, so we're going to start with basically where we sort of left off last session, in which the last thing we looked at was standard deviation. So as you must have noticed, the denominator of standard deviation when you're calculating it from a sample is n minus 1 and not n, which is the entire data, which would include the entire data set. So just want to cover why that would be. So basically, the standard deviation for a sample is what you use to estimate the standard deviation of the population, correct? Because all of everything we're doing is we want to make inferences about the population. Now, generally speaking, the standard deviation is not what is called an unbiased estimate. There's a slight bias. So any standard deviation that you calculate for the sample will always be slightly higher than the actual population standard deviation. So this n minus 1 is a correction that's applied to the formula known as Bessel's correction. But it can also be used to understand or rather illustrate the whole concept of degrees of freedom. So degrees of freedom can be thought of as the number of actually independent data points in the calculation of a statistic. So here we have an example just to illustrate how degrees of freedom work. So let's say we have a little sample of three values with the mean of 45. Now for the calculation of standard deviation, what we need to do is take the summation of the deviation from the mean, correct? So that would be x minus x bar, which is the mean. So we've already calculated x, and now we want to calculate standard deviation. So the first thing we will do is, so we have these three observations. The first one is +2 deviant from the mean. The second one is -10. So now there are certain features of the sample mean. Because this is the sample, the sum of all the deviations from mean has to be 0. We know that. And this the sum of all the observations will be the number of observations into the mean, which would have to make it, because our mean is 45, the total here has to be 135. So now that we've already calculated the mean here, as you can see, there is only one value that this third observation can take. There is no room for flexibility here. So the final, as we can guess, the final observation, it has to be +8, because so that this comes to 0. It's 53 and +8. So technically, when you're calculating standard deviation, there are only, if our n was 3, there are only 2 data points which are free to vary. So technically, there are only 2 independent data points. That is the basic concept of degrees of freedom. And the number of degrees of freedom you get in a sample is dependent on, okay, one second, I'll do it, is dependent on what all you've already calculated. So what you're using to calculate the next step. So for example, since we've already calculated mean out of here, you lose 1 degree of freedom when you're calculating standard deviation. Okay. Now we move on to the concept called standard error. So, I mean, I'm pretty sure that in a lot of papers, you must have heard people refer to standard error. That is what is sometimes reported instead of standard deviation. Standard deviation is a measure of variance, or the measure of dispersion. It kind of tells you how spread around the mean your data is. This is an estimate of a population parameter. It tells you how spread out your data is. But standard error is what you use to kind of measure how confident you are in your estimate of the mean. So let's say I went out there, collected data on like 5 leopards, and I came back and I'm like, okay, the average length of these leopards is, let's say 90 centimeters. Now you might ask me, how confident am I that this is the actual mean of the population? So that is where the standard error comes into the picture. Standard error, the calculation is basically just, it's the standard deviation divided by the root of n. So as you can see, because the denominator is dependent on the number of samples you have, the more you increase sample size, the more confident you can get in your estimate of the mean. and the lower the standard error will be. So first, we'll just like run this for our, we'll run this for our UNCIA data set just to get a hang of how you calculate it and what it actually does. So you can open R now. And okay, we'll open R, and so first things first, as always, open a new script, which you can do by clicking this over here. You'll get a new script, and if your working directory isn't already set, you have to do that. So you can set working directory either through code in the line itself, or you can go, is it in tools? Yeah.
Sorry, it's in session, and you can go to.
Yeah, I'm sorry, I've never set it through the.
In the session tab.
Session tab.
Yeah, you were there. No, above.
Oh, correct. Sorry. Yeah. So you can go to session tab and set working directory.
And choose working directory.
So you can choose a directory. I'm going to choose stats course. Open. Or like what I usually do is I set working directory. You can just run the code set WD and the file path to where you want to set it. Either works. It doesn't matter which one you do. This is only for convenience, basically. It doesn't matter if you set working directory or not. It's just that if you have set it, every time you save a file from R, it will save into that particular folder. Or if you want to read files as well, you can either give the entire file path with the file name, or if you've set the working directory, then you just have to put the file name.
Yeah. You can also add maybe that you can get the working directory. If you're not sure what it is, you can actually type get WD brackets, nothing else, and it will actually return what is your working directory. Sometimes if you're trying to load a file like this UNCIA dataset that we load from time to time, if the working directory is not set to where that file is, R will not find it, and you'll have an error message. So that's also, it might be, most of the time it will be because you don't have the working directory you think you're working with.
Okay. So we get started there. Then the first thing we do is load the file, which, okay, actually, give me a second, I'm sorry. I need to find the file. I haven't saved it in this particular folder.
So just while you do that, yeah, degrees of freedom is a concept in statistics that is always very difficult to get a grasp on, and difficult to explain also. So yeah, just remember that it's like this. It's basically like when you calculate a statistic, which could be simply the mean, for example. So we use that as an example. You will use observations, and the degrees of freedom are simply the number of observations to calculate that statistic that are allowed to vary. So in the example we use, I'll just repeat that in the meantime while Anne is loading the data set.
Yeah, I'm done.
Finish this. Yeah, I can get back to the table. So if you can see, like we had this little example with 3 values. To calculate the mean, you need to take the sum of all these 3 and divide it by 3. If you know the mean is 45, the first 2 values you'll choose can be anything. The third value will be fixed. It has to be something that will sum up to 135 because you need the mean to be 45. These are the degrees of freedom. Is that 2 of these values are free to be whatever they want. The third one will have to be something because we know the mean will be 45. So that's why you have 2 degrees of freedom here, because from 3 observations, only 2 of them are really free to be whatever they want. The third one is fixed. It is not free, essentially. And in the calculation of any statistic, that's what you'll get. There will be observations that are independent, that are free to vary, and others that will have to be fixed because of the way the statistic is calculated. Sometimes, very often, the degree of freedom will be number of observation -1, but not always. For the calculation of other statistics, so not just the mean, but all the things, that maybe will be number of observation -2 or number of groups -1. Or so it depends. It simply will depend on how that particular statistic is calculated. So I know this might not be clear to you right now. So the best you can do at this point is simply to read up on it again if it's unclear. It will not prevent you from doing stats, simply because R will automatically calculate degrees of freedom for you. If you had to calculate any statistic manually, when we start doing hypothesis testing, yes, in the past you have to know how many degrees of freedom you had, and this will be very important for you to do your work. But with R, it's done automatically, which is why if you don't get a full grasp on it, it will not be the end of the world. All right.
Yeah. Just remember, it's the number of independent data points. I'm sure it's not necessarily clear because these two are independent. The third one is dependent on the previous two. So it's, like Guillaume said, not free to vary and, not independent. So that's what you would count as your N. And it's okay, just as long as you kind of get an idea what people are talking about when they refer to degrees of freedom, it's good enough for now.
If anything, it's just good that they hear the term degrees of freedom. It's just good to know that it exists and that it's an important concept. You can look into it later also.
Yeah. Okay, so now first what we'll do is load the UNCIA data set, which I will do with read.csv. And I've already set a working directory. I just have to give it the file name. Control Enter to run the code. Now we have this. We were going to look at standard error, right? So first I will make a I don't need to make a separate object. Okay, so standard error doesn't have a straightforward code to just calculate standard error. So what we'll have to do is we will have to apply the formula for standard error to our data set. So let's say we want to calculate standard error for the length. So what we will do is SD divided by, for square root, it's SQRT, and again the object name. Oh no, it's calculated this for each and every one of them separately. I'm supposed to do that. Let's just
because you need square root of the n, like do you want the length?
Right, sorry, not length of length.
That's fine, that's good for explaining also.
Yeah, okay.
Square root of UNCIA length will calculate the square root for every length, right? Because UNCIA length is a vector of numbers.
What it has basically done right now is, divided the square root of each individual value by the standard deviation of UNCIA length and given us, but that's not what we wanted. What we wanted is this. So the standard error for UNCIA is 1.81. So we can be relatively confident that the mean is close 1.05 plus minus 1.81. So just to demonstrate how it can vary based on sample size, I would like us to extract different numbers of samples from the UNCIA length data set and calculate standard error for each one of them. So I will tell you what we need to do is use the function sample. And can anyone just look up the function, like do the whole question mark sample and tell us how it works? You can switch on the audio.
1.8 is not the standard error. It is actually the, oh, sorry, no, it is the standard error, yes. So we just apply that formula, the standard error being a standard deviation divided by the square root of the number of observations, which in this case, we could get that number by looking at how long that vector is. That would be the number of observations.
So now we're just going to do this like a few iterations of it with different sample sizes in order to look at how standard error can vary based on sample size. So first thing what we will do is we'll create a function for standard error. So R allows you enough, you can write your own functions in R. Now because standard error is not available, we'll make a function to do that, and this is the syntax for it. So first you just function is the function to make a function, and in round brackets you will give it what your input is going to be. We'll just call it X for the time being, and then you start with curly brackets, and inside this is you will tell it what to do. So what we want it to do is take the standard deviation of X and divide it by the square root of the length of X. That would be the number of observations. So now that we have this function, we can just apply it to any number of data points that we want. So has anyone looked up sample yet? Come on, guys. Just
remember, like to look up a function, you put question mark and the name of that function if you want to remember how to use it.
Yeah, so just do question mark sample and you can read out the arguments and we'll just apply it here.
Exactly. So try to look up how to use it and to see if someone could tell us what it does before we move forward.
So does it choose like a random subset of the sample?
Exactly. If you feed it a vector of anything, it will take a random sample from it. So it will, yeah, if you want, for example, a sample of size 10, maybe we put all our length, our vector with all the length, and it will just take 10 random length that we have in our data set. So that's what we want to do. Simply, like, we're going to use that function simply to demonstrate how the standard error behaves depending on sample size. Because as we told you, the larger the sample size, the smaller the standard error should be. So let's just check if it does that. So yeah, the sample function, just to finish on that, is that yeah, you'll need a few arguments. You can see that there is a few arguments available to you in that function. You can set. You will need X. X is not something that is optional. So you need a vector of something. It doesn't have to be numbers. It can be also, it can be any vector, even character vector. You need to, of course, tell it what size it should be. So how big you want your sample to be, R is not going to guess for you. There's no default value here. Replace equal false, that's a default. That means that it will not replace values. If you pick a value, it will not pick it again. Okay. Probability equal null. You do not want, so you want all of these values to be equally probable in being picked. But if you didn't want that, then you could actually set that to something. Yeah. All right. So let's try.
So we're just going to sample. So I'm first going to create a vector with 5 of the samples from uncia.length, and then we can just apply the standard error function that we created. So remember, function initially in round brackets, you will give it the arguments, number of arguments it will have, be only 1. And what this now SE will do is calculate the standard deviation for whatever you give as X and divided by the square root of the number of elements in X. So let's just try that here. We will do SE into test length, which is the subsample that we created. And we get 7.63. We can run this a few times with varying sample sizes. And as you can see, so I started with 5 and got a standard 7.63. Then I turned it to 15. Now the standard error is 5.38. So as the number of samples increases, our confidence in our estimate of the mean will also increase because these numbers will keep decreasing. Now that it's 50, it's 2.07. If you remember, when we did it with the entire length, what we got was 1.819. Okay, so this was just to, like, you guys will get a little bit practice with R, but also just to demonstrate that one of the ways, which I'm sure has been repeated several times, that you can make sure that your estimates are accurate is by increasing sample size. The bigger the sample you have, the more representative of the population that you sampled from your sample is going to be. So I'm hoping no one had issues here. So from here, we will move on into confidence intervals. So now what do we do with standard error? So one of the things we can do with standard error is calculate a confidence interval. Confidence interval is basically a zone, like a range of two numbers within which we are fairly confident our estimate. In this particular case, we will talk about confidence intervals for the mean, our estimate of the mean lies. So Guillaume will explain this bit. You're mute.
Oh yeah, thank you. Also, in the meantime, I guess some people have issues, so we can see what's going on. Anyway, so the standard error is very important because it is actually going to be used to calculate confidence intervals. So the standard error itself is not a confidence interval necessarily, but it will allow us to get these confidence intervals if you've heard about these concepts before. So let's take our data set, the data set that we had already. And let's see. Yeah, so the mean, remember the mean was about 105.2 with our updated data set after we removed the outliers. And it would be nice to know, so not in terms of like how many of the data points we had actually fall within a particular range. Remember that we want to, like, we sample that population of leopards, that we have a sample of leopards, and we want to make inference. We want to understand the entire population as a whole. This is why we do sampling usually. You're not just interested in that particular sample of animals, those select animals that you manage to get your hands on, but you want to understand something about a larger population. And this is what confidence intervals can tell you, is that if we have a mean for our sample, we want to know how confident we are that that mean is around that value, right? We would expect the mean in general for a larger population of leopards to be like around that value, but not necessarily, it won't be that exactly. We already know that if we had more data, we would obviously see, we will definitely get the mean, we'll know that the mean will become something a bit different, but maybe not something extremely different, right? And this is where the standard error comes in. It tells you how confident you are with your mean. And you can get, using the standard error, you can calculate these confidence intervals. So I'll give you an example here so you can see how it works. Okay, the first thing I'm going to do is, we don't need to get back to R. So first thing I'm going to do, can I see the slide? Yeah. Okay. Yeah. Okay. So the first thing we're going to do is create an object that we'll call X bar. That's our mean for the sample. So you see, I just assigned to X bar the mean of uncia length. Okay. Using the function that we created here on the slide, it's SC capital and use smaller. They should use the smaller case. I'm going to create an object, which here I call SE. Do not give it the same name as your function, otherwise it will overwrite it, okay? So sorry for the confusion here. The function is SE with capitalized letters, like uppercase, and lowercase will be the object that I'm creating. But you can call this object whatever you want, of course. That will simply be the standard error for that mean, which we calculated. It will not be exactly what Anne got because she loaded the data set and she did not remove the outliers like we did before. So just bear in mind, if you get a different value from the 1.8?
1.81, I think.
It will probably, I think, should be something a bit smaller.
Yeah, it will be smaller.
Yeah, because the standard deviation was smaller after we removed the outliers. And now we want to calculate the upper and lower boundaries. I don't know. Okay, yeah. Okay, so here I just put like a segment where, you know, with possible length, and I'm gonna plot the mean. This is where our mean is. It stands at 105.2. And remember, as I said, okay, we know that the population mean will be around that value, but we intuitively, we can use intuition to understand this, is that the population, the actual population mean, which we're kind of trying to estimate here, it's more likely to be close to that value and less likely the more you walk away from that value of your sample mean, ideally because you think you have a good sample, right? So the probability of the actual population mean to be like for what value it could be will look like something like this, and it will be actually a nice bell curve, which should remind you of the normal distribution, right? What it tells you is that the probability of the population mean being around our sample mean is really high, you know? But it becomes, the further away you move from that, let's say take 108, for example, it's not that likely. We think it's a lot more likely to be around 105 than to 108. But it's also not impossible, right? If we have a lot more data, maybe we will actually find that it is there. But this is what these confidence intervals will tell you. The formula is this. You will simply, like this is why the standard error is important, because it comes into that equation. It's kind of a constant that will be multiplied by whatever you want the confidence interval to be. So we can calculate the upper and lower boundary of that confidence interval. So typically, statisticians will use a 95% confidence interval to mean that we are this would mean we are 95% sure that the population mean will actually be within that 95% confidence interval that we will calculate. We can of course change that if we want to have a more relaxed confidence interval. We could have a 90% confidence interval, say, okay, we'll be less certain, but the confidence interval will shrink a little bit. So the Q norm here is because in this equation is because this is taken, it should be, we expect this to be a normal distribution. The probability of the mean being something else than that our sample mean to be is going to be normally distributed, meaning it's more likely to be around the sample mean, and it gets less and less likely as you move away from it. The 0.975 is to get that 95% confidence interval. So you can understand here with 0.975 is that the upper interval, I'll just plot them already. If you look at the upper interval, which is the upper boundary is at 108 and the lower boundary is at 102.5. Anything in between has it's 95% confidence. So the area, if you will, of the curve between these intervals is 0.95, and there's 0.25 from either side, okay? Which is why we use 0.975, because it's 1 minus 25%, right? 2.5%. So there's 2.5% of the area that is on either like above the 108, and 2.5% that is below. Okay, I hope that wasn't too confusing for everybody, but just the main thing here is to know that standard error is used in the calculation of these confidence intervals, and we can use that equation here to calculate what this confidence interval will be. And you can adjust the value in the Q norm in the Q-norm argument here, if you want your confidence interval to be more or less relaxed. So 95% is very standard, which is why I use 95% here. You could make it even stronger. You could have 99% confidence interval. So for this, you would have to put 998. Yes. Is that correct? Yes. Sorry, 0.98. Sorry. Yeah, that would be a 99% confidence interval. Right. Okay. The Q norm. Sorry, someone asked if I could repeat what the Q norm is. I understand this is confusing. The Q norm tells you the probability at 97.5% into this curve. Okay. We take 97.5% because we want 2.5% to be left on the right of the confidence interval. We do the same, it's going to be standard error minus the standard error times the same value here. Anyway, the Q-norm part is not what I want you to focus on here. I just want you to understand, mainly that the standard error is used in the calculation of confidence interval, and that's why it's an important statistic. So with these confidence intervals, just to summarize, just to get a good grasp on what we're doing, we are 95% sure that the population mean will be between 102.5 centimeters and 108.0. You could get a value, if you had more data, it's still possible you'll get a value more extreme than that confidence interval. It is just very unlikely. So it's very likely, based on our sample, we can say it's very likely, we're 95% sure that the actual population mean for the leopards is going to be within that range, between 102.5 and 108. If you have a lower sample size, remember the standard error will be bigger. That confidence interval will be a lot larger. So you'll get values that are more extreme. So you can be sure to guess what the mean, what kind of value it can take, basically. All right.
Yeah, and also you have to remember, like a lot of papers will report mean plus minus something, which can be either standard deviation or standard error. So it's very important to clarify which it is, because mean plus minus standard deviation is how dispersed the data is, but mean plus minus standard error will tell you how confident you are that that is the mean, or like the range within which you're guessing that the mean is. So that's one thing that you have to keep in mind. Yeah. So hopefully a lot of these things will get clarified because we will now discuss the normal distribution. So what we're doing in this session is just covering topics that you should know. It'll help you clarify a lot of assumptions in statistics. Okay. So a normal distribution is a hypothetical distribution. You have to remember this. It's a lot of distributions in nature can be approximately normal or mimic normal, but they'll never be as neatly normal as an actual normal distribution is, which is hypothetical. And this is mostly in order for us to be able to apply a lot of things in statistics. So a normal distribution, as you can see here, it's symmetric, it's perfectly symmetric. So the mean, median, and mode are all equal. So the mean is where 50% of the data percentile will lie, and it's also the most popular, let's say the highest frequency number. And you have to remember, this is a probability density function. So it's not this is the probability of the samples being at the mean is the highest, and as you go away from the mean, the probability of those numbers being sampled also decreases. So the total area under a normal distribution curve will be equal to 1, because you can never have more than 1% probability of sampling something. And this will vary based on your standard deviation. So it can be narrower, flatter, but no matter what shape of the normal distribution is, like how flat or sharp the peak is, about 68.3% of the data points will always lie between plus minus 1 sigma. That's one standard deviation. And there are such predictable outcomes for at plus minus 2 standard deviation, you will have 95.4% of the data. And at plus minus 3 standard deviations, you will have 99.7% of the data. And beyond that, the probability of a number belonging to this being sampled will just keep reducing more and more. So as you can see here, this is where that QNorm function for estimating confidence intervals comes from, because if you want about 95% confidence, it's just before 2 sigma. So that's what technically the QNorm function does. So here our UNCIA data set is approximately normal. So things that are normally distributed will be estimates like height, length, so which has a lot of factors playing into it. These will be approximately normal. So there will be some average heights which are very common, and very short or very tall, relatively rarer. So just to visualize our data set, we will apply this formula right now. So just do hist. So that's generating a histogram for the UNCIA dollar length data set. Okay. And if you do plot density, it will basically, so the histogram will give you, one second, I'll just, so the histogram will give you the bins, so which all bins the data falls into. So you can see it's approximately normal, like it's not exactly, because at the upper end, it does not drop off as smoothly as at the lower. And if you do the plot density function, you'll get so this is the probability, like that's been calculated, of the data being in each bin. So I'll pause here because we covered a lot of topics that might be a bit confusing. Does anyone have any questions?
I have one.
Mm-hmm.
For the QNorm, I just wanted to confirm, if our data is not normal, can I still use the QNorm function there?
We will get to that. So the thing is, if it's really not normal at all, then you should not.
The QNorm is really also, it's in the name, it's norm. It's really assuming a normal distribution or something that is approximating a normal distribution.
Normal.
Other kinds of data are not normally distributed. With leopards, you often work with counts. Count data is not normally distributed, so you cannot apply the same there. So it's just that a lot of the statistics that are, let's say, well, introductory to the field it works a lot with normal distributions in a way. Bear in mind though that even also, sorry, yeah?
If it's continuous variables, then they will tend to be normal, or at least approximately normal, and you can apply a lot of things we will discuss. But but for example, for count data and categorical data especially, then these methods will not be appropriate for them.
Okay, got it. Thank you.
Okay, all right, so okay, there's one more question in the chat.
Yeah, okay, so someone asked, yes, some data is not normal. So count data, again, is an example. There are ways to make data normal. So this is one way to circumvent the issue in statistics. You can, for example, use the logarithm. The logarithmic, yes. If you log transform count data, for example, it should become something that resembles a bell curve.
Then you can apply these tools, but then you have to be very careful about your interpretation, because you won't just be able to say, you've applied it to the scaled version of your data, not the data itself. So you just have to be more careful with how you interpret it then.
Exactly. And once you transform it and it approximates something that is a normal distribution, there are also ways to assess if your data is kind of normally distributed. There are tests that do that. You can obviously just visualize it like we are doing right now. We are plotting it to see, we can see, okay, that's not unreasonably, of course, it's a curve that is not symmetrical exactly. There is, you know, something, yeah, it's not exactly normal, but yeah.
Yeah, but the best you can hope for is approximately normal, because remember, normal is a hypothetical distribution. Like, you will never, ever, ever get a normal distribution with real data. It's only meant to help us make certain assumptions and develop tests from there.
Exactly. Yeah.
Okay.
So a lot of the tests that we're going to use make that assumption that the data is normally distributed.
Okay, so now that hopefully everybody knows what a normal distribution is, like, the next step is the unit normal distribution. So this is basically just a normal distribution which has been standardized to have a mean of 0 and a standard deviation of 1. So if you have any normal distribution, it does not matter what the mean and standard deviation are, it can be transformed into a unit normal distribution. And so this is also known as the Z distribution, and this is what is used for the Z test, for instance. And the convenience of this is that because standard deviation is 1 and the mean is 0, if you just transform any data into this, just looking at the value of the data will tell you how far away from the mean it is. So let's say I transform a distribution, like a data sample I have, to the normal unit normal distribution, and one of the data points is 2.9. So without having to actually plot or anything, I can tell that that means that this data point is 2.9 standard deviations away from the mean. You know, it can be plus minus. And Guillaume will go through some of the applications of this. So we'll try to apply this to our data set and look at, you know, how we can visualize and info from that.
All right. I always lose. I'll just ask for
1 second.
Okay, thanks. All right, yes. So just bear that in mind. Yeah, we're transforming our data here. So from any normal distribution, we'll end up with a mean of 0 and a standard deviation of 1. Okay, and then there's some applications to that. That Z distribution is very handy. Change slides. Okay, cool. So what I'm going to talk to you about is the Z-score. This is something you can calculate for every data point that you have. All right. We'll simply apply the same transformation that we would do to make a standard, a normal distribution standard. If you want the mean to be 0, all you have to do is subtract the mean to all of your data points. If you do that, you know, even if your mean, well, in our case was 105.2, you subtract 185.2 to all of your data points, the mean will be 0. Okay. So that's that. Then you just need to divide that by the standard deviation. And the standard deviation will then be 1 by default. And that is your Z-score, okay? So we're just going to do that using the length variable again. Okay, we're going to create an object called X that is going to be the length, the Uncia length, so that vector of numbers. And then we're just going to do very basic arithmetics. We're going to do X minus the mean of X. So this will transform X. It will update X by subtracting all of these values. And we're going to do this again, but this time by taking X again after subtracting the mean. And we'll divide by the standard deviation. And you can check, I didn't do it here, but you can check, you can type mean of X to see what happened to it. You should find something that is not, it won't be exactly 0, I think, just because this is just because of R. Like we dealt with numbers are all, yeah, it was not exact numbers, so that's why we don't get exactly 0. And if you do standard deviation of X, then you'll find 1. I think there you should find exactly 1. Okay, so I call this, I'm going to make another column in the data set just to keep track of that Z-score. I could have just called it z-score actually, but I call it length scale because that whole process of subtracting the mean and divided by the standard deviation, you can also think of it as a scaling process, which is why I just say, okay, this is the scaled version of length. Okay, so it's no longer in centimeters, it's something else. Well, it will be, yeah, it will be. So I'm going to use the object X that I created and assign it to that new column. So I create a new column with using $sign. So I take, okay, Uncia and assign the object X to a column called length scale, and that will automatically create that column. Okay. So if we continue, okay, now we want to, so there was one thing. If you remember, we had these outliers that we simply removed because they were clearly wrong. And then if you remember, we had one leopard that seemed to be quite big and quite heavy. So he wasn't like unexpectedly heavy, like his body weight, like its body weight and body length did match, you know, it didn't have an unexpected weight for its length. It kind of followed that trend that we had from using, well, from our entire, for the entire data set. But it was still like, it did seem like significantly bigger than the other one. So the question here is that, okay, we want to understand what is the likelihood anyway of getting a leopard that is that big using our sample, based on our sample. So let's just look at it. So now remember we have this new column, length scaled. Let's look at that row. So the length for that leopard was 150, was the only one. So we can subset it like this. So we use square brackets here. So the square bracket is going to tell you, okay, which, so Uncia is a data set, it's a data frame, it has 2 dimensions, remember? It has a certain number of rows and a certain number of columns, yeah? We can select the row numbers and column numbers with these square brackets, okay? So Uncia has 2 dimensions, which is where we'll have one index and then a comma and the second index. The first index, remember, is for rows and the second one is for columns. So you can see I didn't put anything after the comma between the square bracket because I want all the columns. I want to look at the entire row for that particular leopard. If I type Uncia length centimeter equal, so double equal 150, it will return a vector of true and false. You can actually type this by itself to check what it does. It's going to be true, like false, 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 true, false. So there's going to be one row for which this is true. And by default, what's going to happen if I put this in there, it will just return to me the rows for which this is true. In which case, that's only a single row, and this is what I would get. So I get, of course, length 150 because that's the rule I applied. Yeah, I get to see everything about that leopard. You could have used the subset function here as well. You can try to apply the subset function that we used before to subset data. That's also possible. So we know that this leopard is from Wakan. We know it's a male, which I guess makes sense if that leopard is going to be a lot bigger than the others. Because I'm assuming male snow leopards are bigger than females. It has a weight of 55 kgs. And length scale is what we calculate. That's a z-score. The z-score is 3.4149. We can say what? 3.1. This tells you that this leopard is just over 3 standard deviations away from the mean. So it's quite far away from the mean of 105. So you see, this is what that z-score does. I can show you on a plot. So this is this is simply a standardized normal distribution, like this Z distribution that we saw. This is going to be our 95 confidence interval, similar to what we did last time. And I just plotted all our data points so I just plotted the length on this x-axis to see where they are, basically. So of course, you can see that most of our data points fall within that 95% confidence interval, okay? Which will be the, it will be exactly, if you remember that graph that we had.
You can just go back.
Oops. What I want to show is this. Okay, so remember, this is the Z distribution, and it tells you how much of the data, how much of the density is within a particular range. And you can see that at 2 standard deviations away from the mean, minus and plus, if you take plus or minus 2 standard deviations away from the mean, you get 95.4% of all the data, of all the probability. But if we want a 95% confidence interval, of course, it would have to be slightly less than 2 standard deviation, because here we have 95.4 and we want 95. The answer, actually, there is a number to this. It's 1.96 standard deviation will be to get exactly 95% confidence interval. So just to remind you, this is what I did there. Okay, so again, so this will be exactly at 1.96 standard deviation, which means that the area here will be exactly 0.95 or 95%. The remaining area is 5% together, so 2.5% here, 2.5% there. That's the area. That's the kind of like the density probability of getting leopards from there. So yeah, again, we can plot our data. Not surprisingly, most of them are within that confidence interval, because it's 95. There's 95% chance every time to get an observation within that range. And here we can see our outliers. There's one actually to the left. We didn't realize we had that one. And of course, to the right, this is our big leopard. It's the most extreme in the positive around the mean. So it's much bigger. It is much bigger than the mean. And we calculated with the Z-score that this would be exactly 3.149 and so on, standard deviation away from the mean. So it's a measure of how far it is from the mean. We can translate that into a probability, right? Of course we can, because we know already that here is like
95.
Yeah, 95% possible. Yeah, there's a 95% chance to get leopards from that range. And of course, there's only 2.5% chance of getting a leopard bigger than that, right? On the right-hand side. So this is the probability here, is 2.5% of getting any observation within that range. And that leopard is even is quite to the right? So it's going to be very unlikely to get a leopard like this. Let's calculate it. If you calculate that probability, it is going to be, so this is the probability for that particular Z-score. And yeah, we don't need to get into the whole how to calculate that probability at this point. But I just wanted to see, whoops, what is going on?
Sorry.
Perks of Zoom.
Yeah.
Can you get back to it? Because
yes, you should have it now. Okay, so
no,
there was a question. Oh, you're not done. Sorry.
No, can you get back to it?
Oh. Yeah.
Okay, thanks. So simply, yeah. So there is this Z-score of the 3 point something would translate into that probability of getting that observation. There is 1 in 610 observations that will be that extreme. The question is, okay, does that make this an unreasonable outlier? Not necessarily. It just tells you, okay, that's the likelihood of getting a leopard that size. But we have a sample of 100. Maybe it's not that unlikely that some values will be that extreme, and that's what we get. All right. Okay. So this is simply to really gently get you into the whole understanding of confidence intervals and what we would consider something to be too extreme compared to what we would expect, and that's really is the basis of hypothesis testing, which we'll get into in a bit.
And so there was this question that, so the Z transformation is not transforming the data into a normal distribution. Like you can First of all, it's useful only to apply the z-score to something that is already kind of normally distributed. It's to allow you to sort of interpret your data much more easily, like THEOREM just did. For example, for the value of this 150 length leopard, now we know that 3.14 means it's 3.14 standard deviations away from the mean. So it's more for ease of interpretation and access. And log transformation is actually transforms your data. So the distribution could look like something else, but doing the log transformation will change the distribution of the data. This is not changing the distribution, it's just scaling it.
I guess we will talk maybe in the next sessions about like different other kinds of data that are not normally distributed and what it implies. As I said, the Z transformation, it goes from a normal distribution to something that is also a normal distribution. It's just that the Z distribution is a scale distribution. It's standardized, right? The same way you could convert like inches into centimeters, because maybe it's more standard.
Or more easily, let's say you have two populations that you sampled, which are both normally distributed, but with different means and standard deviations. Transforming them both into a Z distribution will make it easier for you to compare the two. Okay. And so we're not going to really cover it, but so that you know, that based on the Z distribution, there is also something called a Z test, which is one type of hypothesis testing. But a Z test is only applicable if you know the population mean and standard deviation. If you have that data, then you can use it to test if your sample is from the same population or not. Okay, these will get clearer as we move on. So then next we will move to the central limit theorem. So this is sort of like the basis of most of the parametric tests and that you will come across, which deal with calculating mean and standard deviation. So the central limit theorem states that if you take the sampling distribution of means, what I mean by that is, let's say there is the population of leopards at Wuhan, and you sample 10 leopards out of that, then you sample 10 leopards out of it again, and then again, and then again, and you calculate the mean for each one of your samples, and then create a histogram for that. That is called the sampling distribution of means. Okay. If any of this is not clear, just please ask immediately. So it says for the sampling distribution of means for any population, regardless of the underlying distribution. So let's say that the population is uniformly distributed, or it doesn't matter what the distribution is, the sampling distribution of means will approximate a normal distribution, and it will approximate a normal distribution even more with increasing population size. Okay, I mean, we'll move on to just testing this once I've done with this thing. And there are certain features of the sampling distribution of means. So the mean of this distribution will be equal to the population mean that you sampled from. And the standard deviation of this distribution is basically the standard error. So the standard deviation of the sampling distribution of means will be equal to the standard deviation of the population mean divided by root of the sample size. So you can create a sampling distribution of means for different sample sizes, and they will all look different. So the smaller sample sizes will not actually be very normal looking, but the larger your sample size, the more this distribution will resemble a normal distribution. And this is what is used as fundamental for applying a lot of these tests that we will do to all kinds of data. So the implication, like, it's very important to note that it does not matter what the distribution of the population is, sampling distribution of means will always be approximating normal. So because of which we can apply a lot of tests that assume normal distribution to other types of distributions as well. Okay, so just for us to be able to visualize this, we'll now, we'll just go to R1s and let's just try this out. Let's create a, so I already have this thing here. I'll explain parts of the code. So this is just to plot density function of, so our UNIF, what it does is it will randomly sample out of a uniform distribution. So I'm using a uniform distribution, not a normal distribution, so that you can see what happens. So 100 is the number of samples it will take, and then I've given a minimum and maximum number. And what this little bit is doing is I've just written a function to automate the sampling and the creation of the histogram. So actually, I'll just do a.
I just want to clarify here. You do not need to know this code. This is simply like,
yeah.
You need to understand what we're doing here. So can I just like explain one, like to just this central limit theorem, of course, is going to sound very confusing to a lot of people. So just to like explain before we actually do this in R, let's just give an example first, like this, and then we'll do this in R to understand. So to understand what we're doing. The idea with this central limit theorem, and you can think of it using, for example, the data set that we already worked on. Assume for a second that the data we were using was not normally distributed, okay? Well, we have what, just over 100 observations for size. If you take a sample from that, let's say we take a sample of 10, we take 10 leopards, we look at their size, and you calculate the mean of that. You repeat that again. You take another sample of 10, maybe, and you calculate the mean again. Of course, the means will not be the same, right? They will be maybe close, but not exactly the same. You repeat that again and again. You every time take a sample of 10 from these 100, and you calculate the mean. The idea is that the mean of means will be very close to the population mean. It will approximate it. The other thing is that if you look at how frequent these means are, so this is what we call it, a population of means. No,
sampling distribution of means.
Sampling distribution of means. Thank you. This is what it is. It's a population of means. It's like you take a sample, calculate the mean. Take another sample, calculate the mean, and so on and so on. So the means become your data set, basically. And if you were to plot this, you would realize that they are normally distributed, and the peak will be very close to what the population mean actually is.
So the translation. Oh, Mohammed cannot. Can everyone else hear us?
Okay, someone is having trouble.
Yeah, we can
with
hear
the audio.
Okay, maybe something is wrong with your speakers if you cannot hear us. But just to finish on that, is just to just reiterate what Anne already explained, but we will never explain this enough because it's not necessary.
Yeah, it's a little confusing, but also important.
If you do that, of course, if you do that, okay, it makes sense. You apply this to data that is already normally distributed. Okay, maybe you think, okay, it's not surprising that this will be also normally distributed. But if you apply this to data that is not normally distributed, the mean of means will be normally distributed. And this is where the central limit theorem is very powerful. Is that for any kind of distribution, it could be the weirdest distribution you can think about. Like it could be like a curve going like up and down, like rather than having a bell curve, it could go like up and down. It could be like a flat line. If you take means of means, it will always be normally distributed, which is kind of crazy.
Yeah.
But now we want to demonstrate with a real example. So what Anne will do with this code is she will generate data that is not normally distributed and apply this central limit theorem to demonstrate to you what happens. And you will see that the mean of means is normally distributed, even though the data itself is not. Let's do it.
Yes. So basically, just so everybody knows what this function is doing is it is sampling from a uniform distribution. So that means every value is there in the same equal number of times. There's no variation in the in the distribution itself, and the values can range from 0 to 1. So the mean will be approximately 0.5. Okay, and what X is doing, I'm just changing the number of times, the number of data points that we are like extracting from the uniform distribution. So we will do CL test. So this is by taking a sample of 10 out of our uniform distribution. This is what it looks like. So even at 10th, remember this is a uniform distribution. So the probability of getting a 0 is exactly the same as probability of getting a 1 or anything in between. Okay, and it still comes into this little, when you plot the means of all of our samples, it still comes into gives us what's a normal distribution. Now let's increase the sample size to 50. Okay, it's not looking so normally distributed anymore, I guess, but 100. So what I'm doing is increasing the sample size. So each of these histograms is a histogram of the mean of 100 samples with first one 10 samples, 50 samples, 100 samples. Now it's 500 and finally 2000. So as you can see, as we increase the sample size, the distribution is getting more and more normally distributed. That's with 5,000 samples. Yeah, and this was a normal distribution. It wasn't a sorry. This was a uniform distribution that we sampled from. It wasn't a normal distribution. So you can see that this applies irrespective of what your underlying population distribution is. So basically all it says is if you repeatedly sample, then most of the samples will give you the population mean. And this is what the distribution will be.
Can you plot, actually, I don't know if you showed us that already, plotting the actual density of the sample that we took from, like that sample we sampled from?
The sample, oh, the density of the sample we sampled from. Okay, yeah.
Just to show what it looks like.
Yeah, this is what we sampled from. So this is the probability.
So this is just like a random, like it's really just a random sample. This run, don't worry about these functions, like this code, you don't need to understand. This is really, we're using R to demonstrate the essential limit theorem. Don't worry about understanding that code. Like it's a bit more advanced stuff. But essentially, just bear in mind what we do here is.
This is what the population looks like.
Exactly.
Not
think of it like, okay, what is it? We took a sample. Yeah, we like this, what this line does, line number 20, is that it will generate a sample with values from 0 to 1. So any values from 0 to 1. It will, the uniform, it's from a uniform distribution, not a normal distribution, which is why it's a R unif in there. Meaning that all the values from 0 to 1 that we want to sample, they all have an equal probability. Think of it like, just think, for example, like rolling a dice. If you roll a dice, all the values on the dice have the same probability. There shouldn't be a higher chance of getting a 6 than getting a 1. Or they all have an equal probability of being picked. We could actually do that with the dice, actually, also. You roll your dice and you count how many of each number you got, and that's it. So the data will not be normally distributed. You won't have one value more common than another. But if you sample now, you take like random samples from what you got, maybe you roll the dice 100 times. You take like 10 instances of your dice roll, and you calculate the mean. And if you repeat that many times, like that's what we did in this loop there, using that function. So this is a function that Anne created to just do that automatically without having to rewrite the code every time. So you repeat that and you take the means of the means, and the mean of the means will be somewhere in the middle.
So for example, I've just changed this. So it's, 0 to 1, it's now 1 to 6. So like a die roll. And again, this is with 10. So the mean, the highest point is it's increasing a bit, is around 3, as you can see.
And that's what you expect. What you would expect it to be around 3.5 for that.
Yeah.
So the average value for a dice would be 3.5. And what's interesting is that even if it's a dice roll, it is more likely to get a mean closer to 3.5 rather than something extreme. That's why it's normally distributed in the end, even though that dice roll is not data that's normally distributed in the first place. Okay, I guess that's it. So yeah, again, just to, I think something we should say is that, yeah, the central limit theorem is a very important theorem in statistics, and everything, a lot of the things that we will learn derive from it, which is why we feel like we do have to mention what it is. But don't worry, you don't have to apply this yourself directly. Right?
Yeah. No, yeah, you never have to actually apply it. It's just so you know, because this is, in a lot of cases, the implicit assumption for many tests. You don't actually have to apply it in the test itself, but this is where all the logic of it is coming from. So I hope that's clear. And does anyone have any questions regarding the central limit theorem? If not, then we'll carry on.
We can maybe take actually maybe 5 minutes to answer questions.
Yeah, we can take a, yeah.
Okay, and if you don't have any questions, or if you can also, I guess, take a little break, about 5 minutes.
Mm-hmm.
All right, so any questions so far?
Relook at the sampling distribution of means. You mean what we did in art? So you can just turn on your mic and ask the question. So we're like in a 5-minute break, you can just ask. So do you mean on R?
No, this is just about when you talk about the mean being the population when we do a central limit theorem. What is the significance of sampling distribution of means? That is the question.
Yeah, so significance is that because of this, even if the underlying population is not necessarily normally distributed, sometimes you can, some tests you can also apply to other types of distributions because of the sample. Like even if it's not normally distributed, the mean itself is normally, means are normally distributed. And so also, as you can see, this whole concept of standard error also comes from this. So the standard deviation of the distribution of means is equal to standard error of a population, of a sample, let's say, because it's square root of n. And it's the implicit assumption in a lot of tests. So for example, the t-test, which we will get to right now, it's based on the central limit theorem. Why can you compare two different population sizes? That comparison is coming from the distribution of means.
But again, just to make, to reiterate, is that you don't need necessarily to understand the central limit theorem to apply a t-test. You can still do a t-test the way you are taught to do it. But I guess, but this is where it comes from. That's kind of the origin story of the t-test and lots of other tests.
Thank you.
Do you have any other questions? Maybe also R-related questions if you're struggling with the coding?
Yeah. Oh, so Faye had some trouble with line 14. Here, this one.
That was a while ago, actually.
Yeah, I know. But did it work out, Faye?
Are you still here, Faye? Hi.
Maybe not.
Oh, okay, it didn't work. Do you want to unmute yourself to maybe other people had the same problem? Okay. Actually, okay, Rohit has a question. He's asking whether you've heard about what bootstrapping is, whether this is also deriving.
Yeah. So I'm not sure if bootstrapping is deriving from the central limit theorem, because it can be done for any kind of a test. Bootstrapping, yeah, I guess it's basically to make sure that your estimate is correct. So the more number of times you do it. So I've actually not done bootstrapping myself. I just know what happens. It depends on the test, I would say.
It's a good question. Yeah, I would not be surprised if it was really directly related.
Yeah.
To the central limit theorem, simply because it is the same process, right? You are subsampling and you do that many times and your estimate will usually end up being more accurate. So I would say yes, but simply because, yeah, the process is the same. Yeah, so the properties of the central limit theorem may be applied in that way.
I have a question. So just to reiterate the sampling distribution of means. So for example, there's a population and I took 2 samples and then for those means, I'm now creating a distribution, right? The means of those samples, sample 1, sample 2. I create a distribution and then those are kind of normal, isn't it?
Yes. So you wouldn't really get a normal distribution with just 2 means, but like the more means you add to it, it will take on the shape of a normal distribution.
Right. But again, in practice, if you simply want to compare 2 samples that you have, like maybe, actually, we will apply this when we do the t-test. You don't have to do that process. Again, we're not going to apply the central limit theorem directly, but we will use tests that are derived from it. The t-test is one of them. If you apply a t-test, you will compare 2 means. You will have one sample with a mean, another with a different mean that will be either bigger or smaller. And maybe you want to find out if these are they statistically equal or are they actually statistically different from one another? So in practice, you won't be doing this subsampling that we just did.
Yeah.
But we will apply the t-test later, which is, of course,
this is more so that you know, if someone ever alludes to this, this is what they're talking about. And there are many assumptions out of this, which is what tests are based on.
Yeah, because we hear so many times, but I think every time I somehow forget what is this, but then I want to remember this.
Okay, so the mean of means will be equal to population mean. Just remember that.
Oh, yeah.